Welcome back everyone. In this lecture I will actually talk about what is called abstract Jordan decomposition for elements of semisimple algebras. So, let us first recall what is this Jordan-Chevalley decomposition, and then we will actually slowly get into semisimple algebras. So, recall. So, given operator T of acting on some finite dimensional vector space V. So, we can write T as sum of two operators S and N, where N is being semisimple, S is being semisimple and N is being nilpotent. Not only that, so this is actually written in a unique way. So that this T and S commutes and N and T again commutes and S and N they also commutes. Okay. So, this additive version of this operator being written as semisimple and nilpotent operators will be called Jordan-Chevalley decomposition. So, we would like to talk about similar decomposition for any elements of the semisimple algebras. Okay. So, if we recall from SL2 theory, so what we proved, so if we take this SL2 representation, SL2C acting on let us say V being finite dimensional representation of SL2. So, what we have seen, so this means we have a map from SL2C to V. Okay. We indeed proved if we take this H and then look at the action of H on capital V. So, this is actually diagonizable. So, this is what we proved when SL2C acts on this finite dimensional representation, then phi of H acts diagonalizably. Similar to that, phi of X and phi of Y both act nilpotently, okay, nilpotently on this capital V. So, this is what we proved for SL2 representation theory. So, we would like to prove very similar statements for semisimple algebras. So, let me state the result, okay, because then we will not be lost, because we will be talking about two different notion of Jordan-Chevalley decomposition. So, I do not want you to get confused. So, let me just write the result and then I will actually explain what we really mean. Okay. So, what we do, we take G being semisimple algebra, okay. Again we also take a representation of G which we call it phi. So, which is a map from G to GL of V, where V is actually one assumes to be finite dimensional representation. So, now we can actually talk about what is called this Jordan decomposition of each images of these elements of G. Okay. For any x in G, we can talk about phi of x. So, this is as being element of endomorphism of V, this has what is called this Jordan-Chevalley decomposition. So, this phi x one can write it as some, let me call it again capital S and capital N. So, this phi x can be written as capital S and capital N, where S is being semisimple and N is being nilpotent. So, this is Jordan-Chevalley decomposition of this phi x inside endomorphism of V. Okay. But suppose if you have already started G as some linear Lie algebra, okay, let us say G is already sitting inside some GL of W. Okay. So, then we can also talk about Jordan-Chevalley decomposition of this element x in G inside GL of W. Okay. So, you take this x in G as being element of GL of W, you can write x as xs plus xn. This is again Jordan decomposition inside your G or your GL of W. Actually, the first conclusion is this both xs and xn. So, they all will be elements of your G. So, in particularly we are talking about Jordan-Chevalley decomposition inside G only. Not only that, if we look at this phi x equal to phi xs plus phi n, phi xn. So, this is going to give us some decomposition of phi x into some maps. So, we will prove that this decomposition will be actually will coincide with the decomposition that you get it from Jordan-Chevalley decomposition of phi x inside endomorphism. Okay. So, indeed what we want to say, in some sense, if we know that given element x in G, it is already nilpotent element inside your linear Lie algebra, then you can guarantee that it must act nilpotently on any given representation. Similar to that, if given element is already semisimple element in your linear Lie algebra, then you can guarantee that that element should act semisimply on any given finite dimensional representation. So, this is very similar to what we have in SL2. So, here H we know already semisimple as element of SL2C and x and y both are nilpotent as element of SL2C. But now what we proved, so if you look at the action of H on any finite dimensional representation, that should be semisimple. Similar to that, this x and y also act nilpotently on this any finite dimensional representation. So, indeed we want to actually connect all these dots and then relate this with what is called this adjoint representation, which is add G, which is isomorphic to G. Okay. So, that is our ultimate goal. So, to do this what is called this abstract Jordan decomposition and the usual Jordan decomposition. So, what we will do, so to talk about abstract Jordan decomposition, we will use this adjoint representation. Okay. And then for any abstract semisimple Lie algebra, it makes sense to look at what is called this add of G, which will be isomorphic to G. But one advantage for add G, that is actually subalgebra of this GL of G. Okay. That way we can talk about usual Jordan decomposition of that. Okay. So, let us see what we are doing. So, here is what I want to do. You start with G, which is semisimple Lie algebra. So, this is just abstract semisimple Lie algebra. So, nothing given. So, we know that there is this add map which actually maps G to GL of G. So, indeed what is the image of this add G? So, that is just add of G. Okay. We have seen that this add of G is indeed sitting inside what is called the derivations of G, okay, which is sitting inside GL of G. So, now for given element x in G, one can look at add x. So, which is an element of add G. So, since add G is sitting inside endomorphism of G, okay, one can talk about Jordan-Chevalley decomposition for add x. So, which we denoted by capital S and capital N. So, this is Jordan-Chevalley decomposition. Indeed, what we will prove, so we will prove in a minute, we will prove that add G will be equal to the derivation G, and derivation G must contain all its elements, semisimple part and nilpotent parts. Okay. So, in particularly if we assume this result, then this add x you have written as s plus n, this is the usual Jordan decomposition. So, then this s and n both will lie inside the derivation g, but derivation g is nothing but add g. So, that would imply that this s is inside add g and n is inside add g. Now, g2 add g is actually 1-to-1 correspondence. So, that means there exists xs in g and xn is in g such that add xs will be equal to capital S and add xn will be capital N. So, now if you go back to what happens inside g, x is written as xs plus xn and add x is written as add xs plus add xn. Okay. Now, the way we have chosen xs and xn, so that this add x equal to add xs plus add xn becomes the usual Jordan-Chevalley decomposition. Okay. So, in this case we actually say that this xs plus xn is the abstract Jordan decomposition of this x. Okay. So, this decomposition is called abstract decomposition of Jordan-Chevalley decomposition of x. So, note that this xs and xn both must be unique, because if we because the usual Jordan decomposition of add x will be unique and the add map is being 1-to-1 correspondence. So, we will get xs xn being unique. Okay. So, these to define even the abstract Jordan decomposition, we need this fact, couple of facts. One is derivation of g contains all its elements semisimple and nilpotent parts, and add g is actually equal to derivation g when g is semisimple. Okay. So, this is what allows us to define what is called the abstract Jordan-Chevalley decomposition. So, later we will see that if we start with g being a linear Lie algebra which is also semisimple, then there is a usual Jordan decomposition for each element of g. Okay. So, in that sense, okay, we can ask this question whether there is this usual Jordan decomposition and there is this abstract Jordan decomposition, whether they coincide or not. So, it is a fact they coincide. So, indeed we do not get a two different decomposition. So, that is a beauty of this entire theory. Okay. So, before getting forward, we will actually prove the facts that I already promised. So, let us write it as a proportion. So, we take G being finite dimensional complex semisimple Lie algebra. So, then what one can prove? We can prove that the add of G must be same as derivations of G. So, this is just follows from the fact that one can talk about usual Jordan decomposition for element of derivations of G. Okay. So, let us see how one can prove. So, since this add maps G to this add G 1-to-1 correspondence, okay, one can add G is also actually ideal inside derivation G. One can view this derivation G as module for add G. Okay, that is what we are going to do. So, note that. So, this is the computation we already did. So, if we take the bracket delta comma add x, So, then what we get is just add of delta of x, and this is true for any delta in derivation g and x in g. Okay. This identity is something that I already checked. So, if you are not comfortable, you should check again. So, now look at this add map from g to this derivations of g. Okay. So, now the add g is an ideal inside derivations of g. Okay. And this is actually true for any Lie algebra, there is nothing special about semi-simple. So, now if you look at the center of g, so that is being solvable ideal, that must be 0. So, that implies g must be isomorphic to add g. Okay. So, that is something we have for semi-simple algebra. So, now what we are going to do, so we take m to be this add g, so which is sitting inside the derivations of g. So, now the killing form of g, okay, is being non-degenerate, tells us that the killing form on add g is also non-degenerate. Okay. So, in particularly the dimension of this derived algebra, so that will be equal to the dimension of this m and then dimension of this m perp, okay, because the killing form restricted to m will be the killing form on m, okay, and that is non-degenerate. So, we get this dimension matches. So, to prove that add g is equal to derivation g, it is enough to prove that the dimension of this m perp is 0. Okay. So, it is enough to prove that this add of the dimension of this m perp is 0. So, m is being ideal. So, the killing form is actually on m is the restriction of the killing form on derivation of g. So, now we can use this Cartan's second criterion. Okay. So, that says that the killing form on m, so this is actually non-degenerate. So, in particularly if you look at this m intersection m perp, okay, so that must be 0, because m intersection m perp, that will lie inside the radical of the killing form, okay, but the radical of the killing form is being 0, that would imply that m intersection m perp is 0. And now if you think about it, so then this will imply that the bracket of m and m perp, that must be 0, because the bracket of m and m perp, that will lie inside m intersection m perp. So, now what we do, we take some delta inside m perp and add x inside m. So, then we know that the bracket delta comma add x, so that is 0, but the bracket delta add x is nothing but add of delta x. So, this is being 0, but add is being 1-to-1 map, that would imply immediately that delta x is 0. So, now we proved that delta x is 0 for all x in g. Okay. So, that implies delta must be 0 as a map. So, that means m perp is 0. So, that proves that m is same as the derivations of g. Okay. So, this is something repeatedly uses the Cartan's second criterion and so on. Okay. But indeed what we have proved, if we take g being finite dimensional complex semi-simple Lie algebra, then add of g must be equal to derivations of g. And it is a simple exercise to show that given any derivation, if you take its Jordan-Chevalley decomposition, the usual Jordan-Chevalley decomposition, then both that semi-simple part as well as nilpotent part, they will be again derivation. So, that I will leave it as exercise. So, I will just state it as exercise. So, you start with g being complex Lie algebra. So, now this is nothing to do with semi-simplicity, it is just true for any complex Lie algebra. Take G sorry delta being element of derivations of G. Now, since derivations of G sits inside endomorphism of G, we can talk about delta is being equal to delta S plus delta N. So, this is the usual Jordan-Chevalley decomposition. So, now what is our claim? So, then prove that this delta S and delta N both are actually derivations of G. Okay. So, it is enough to prove it for only delta S, because delta N being difference between delta and delta S, we get delta N for free, okay, because derivations of G is a subspace of endomorphism of G. And again this is a simple exercise, because if you take V lambda being, so let us say G lambda being lambdath generalized eigenspace. So, this is lambdath generalized eigenspace. So, then what one can prove, if we take the bracket between this G lambda and G mu, okay. So, this is lambdath generalized eigenspace with respect to delta. So, then you can see that the bracket G lambda G mu, this has to be subset of G of lambda plus mu. So, now use this information to prove that delta S must be actually derivation. Okay. So, I will leave it to you to check. So, now using this fact, you can see that for any element of the derivation of G, if we take this usual Jordan-Chevalley decomposition, both the semi-simple part and nilpotent part, they are elements of these derivations of G. So, now if we combine all the results that we have, so if G is semi-simple, so then we have that add G being equal to derivation G. So, now given any x in G, we can talk about add x being equal to add xs plus add xn. This is the usual Jordan-Chevalley decomposition. If we take this as usual Jordan decomposition, then we say x is being equal to xs plus x1 is the abstract Jordan decomposition. Okay. So, indeed we will prove that if we start with this abstract Jordan decomposition, even for any linear Lie algebra which is semi-simple, okay, we can talk about usual Jordan decomposition for that particular linear Lie algebra. For example, SL2C. Okay. If we take SL2C, this is inside M2 of C. So, given element Z inside SL2C, one can talk about Z is being equal to some Zs plus Zn. This is the, let us say, usual Jordan decomposition. So, this makes sense because the trace of Z is being 0 implies that trace of this Zs is also 0, because trace of any nilpotent operator is 0. So, that implies that both Zs and Zn, they are element of this SL2C. So, the linear Lie algebra which you start with, that may be closed under already the usual Jordan decomposition. So, in that sense we can also talk about what is called this abstract Jordan decomposition, that being like add Z, you write it as some add Z dash plus add Z n dash. So, now the question is whether that abstract Jordan decomposition coincides with this usual Jordan decomposition that we already have. Indeed, it coincides. So, that is a big theorem. So, let me state it here. You start with what is called semi-simple Lie algebra. Semi-simple Lie algebra, and let us say you have a map theta from G to GLV. Okay. So, this is a representation, be a representation of G. So, now we have what is called abstract Jordan decomposition for any element of G. Okay. So, for x in G, you can talk about what is called this xs plus xn, which is abstract Jordan decomposition. So, what is this abstract Jordan decomposition? You look at add x, then add xs plus add xn becomes the usual Jordan decomposition for add x. So, that is the definition of abstract Jordan decomposition. So, now then what we want to prove, we can look at what is called this theta x being equal to theta xs plus theta xn. Okay. So, we want to claim that this is indeed the Jordan decomposition of theta of x. This is the usual Jordan decomposition, Jordan-Chevalley decomposition of theta of x. So, this is actually a big theorem. So, in particularly if for some reason if you know that given element is already semisimple, add semisimple, then it must act semisimply on any finite dimensional representation. Okay. For some reason given element is already add nilpotent, so then it must act nilpotently on any given representation. So, this is the corollary. Okay. So, if given x in G is add semisimple, so then x must act semisimply on any given finite dimensional representation of G. Similarly, if x is in G is add nilpotent, that is add x is semisimple. Similarly, add x is nilpotent. Then x must act nilpotently on any finite dimensional representation of G. So, this is very important corollary. This is indeed only true for semisimple Lie algebras. So, the proof is again like understanding the definition of both abstract and usual Jordan decomposition. So, let us go through very slowly and then try to prove this statement. This is a very important statement. Okay. So, if we start with some element x, so we just say we write it as x equal to xs plus xn. Okay. So, first of all we can actually go modulo the kernel and then we can assume this theta being actually injective. So, let us not worry about it, let us just work with theta, it is not a problem. So, let us take theta, so which is a map from G to GL of V. Okay. So, we have this kernel theta. So, then G modulo kernel theta, so this is being isomorphic to image theta. So, this must be semisimple Lie algebra. Okay. One can talk about abstract Jordan decomposition of elements of image theta. Okay. So, there is no issue with that. So, image theta is already sitting inside GL of V. Okay. So, now if we take x being xs plus xn, so let us say x is in G. So, this is the abstract Jordan decomposition. So, then what happens? It is not that hard to see if we take this theta of x, so that must be equal to theta of xs plus theta of xn. So, this becomes abstract Jordan decomposition of theta of x. This becomes abstract Jordan decomposition for theta of x. So, how one proves this? One can directly check what are all the properties that you required. For example, so what is this definition of x being xs plus xn is abstract Jordan decomposition. So, x equal to xs plus xn. So, this is abstract Jordan decomposition. So, this implies if you look at add x, then add x is being add xs plus add xn. So, this is the usual Jordan decomposition. Okay. If you look at this, if you apply theta and then you can see that you get from this equation add of theta of x is equal to add of theta of xs plus add of theta of xn. Okay. So, now you can see that, so this is actually the usual Jordan decomposition of this add theta x. Okay. This is something I will leave it to you to check. So, check that this is usual Jordan decomposition of this add theta x. So, now because this is actually usual Jordan decomposition of add theta of x and this is uniquely defined because all these are inside the image theta. So, you can see that we are talking about Jordan decomposition inside the image theta. So, that implies that this theta of x is equal to theta of xs plus theta of xn. So, this is the abstract Jordan decomposition for theta of x. Okay. So, now this actually tells us that if we prove, if we have G being subalgebra of GL of V, okay. So, then for given x in G, if x equal to xs plus xn is the abstract Jordan decomposition, if it coincides with the usual Jordan decomposition, then we are done, because any abstract Jordan decomposition of this theta of x, so which is inside this image theta, which is like g dash, let us say g dash. So, then the abstract Jordan decomposition of this element theta of x of g dash coincides with the usual Jordan decomposition of theta of x. So, that is what we wanted to prove. Okay. So, that is the main theorem for us. So, this is coincide with the usual one. So, that means for any linear Lie subalgebra, which is semi-simple linear Lie subalgebra. So, what we need to prove? We need to prove that the abstract Jordan decomposition coincides with, so we need to prove that the abstract Jordan decomposition coincides with the usual Jordan decomposition. Now, uniqueness will take care of rest. Okay. So, how one can prove this? So, let us say x equal to xs plus xn, this is the abstract Jordan decomposition. Then we need to prove that this is the usual Jordan decomposition, but by definition you can see that if we start with the usual Jordan decomposition, okay, let us say x equal to s plus n. This is the usual Jordan decomposition. N is nilpotent would imply immediately that add n is nilpotent. Similarly, S is being semisimple would imply that add S is semisimple. So, in particularly if you look at add x as a map on GL of V, you get add x equal to add S map on GL of V plus add n map on GL of V. So, this becomes actually the usual Jordan decomposition, the usual Jordan decomposition. So, now if you restrict this to G, so then you can easily see that, so this also becomes, if you restrict to G, this also becomes the usual Jordan decomposition. So, that means this x equal to s plus n is actually the abstract Jordan decomposition. So, now uniqueness of these Jordan decompositions will actually tell you that the abstract Jordan decomposition coincides with the usual Jordan decomposition. Okay. It is basically understanding the definitions, so nothing else. So, but it proves what is important is that the statement. So, if we start with abstract Jordan decomposition of this x and then look at any representation of G acting on some finite dimensional vector space V, then if you take the image of this abstract Jordan decomposition, which is theta of x equal to theta of xs plus theta of xn, then that must be the Jordan-Chevalley decomposition of theta of x, in the usual sense. So, what is important is that if you take add semisimple elements, that should act semisimply on any finite dimensional representation of G. Similarly, any add nilpotent element should act as nilpotently on any finite dimensional representation. So, these two are very very important corollaries which will be used later in developing this the theory of semisimple algebras. Okay, I will stop here. In the next class, I will actually start with the structure theory of semisimple algebras. So, we will use all the results that we have learned so far. So, I recommend you to actually revise the results before starting the next lecture. Thank you very much. Thanks.